Hi students, in this video we are going to see about the velocity of waves in different media. Let us case if you struck a hammer on long rails at a distance, when a person keeps his ear near the rails at the other end, the person will hear two sounds at two different instances. Do you know why this happens? Because in this case, as the hammer is kept at one end, the sound produced by the hammer passes through two medium, one through the rails and the other through air. So the person, when he keeps his ear at some distance away from the position of the hammer, he or she can able to hear the two sounds at two different instances. The sound that is heard through the rails, that is through the solid medium. The sound traveling through the solid medium travels faster than the sound we hear through the air, that is through the gaseous medium. This shows that the velocity of sound is different in different media. In this topic, we are going to derive the expressions for two different cases. First one, the velocity of transverse waves along a stretched string. Second one, the velocity of longitudinal waves in an elastic medium. First of all, we can derive the first case, the velocity of transverse waves in a stretched string. Now we are going to compute, we are going to derive the expression for velocity of transverse traveling waves on a string. Let us take a string and keep the one end of the string fixed to a support and keep the other end of the string in your hands. When you give a small jerk to the string at one end, that is, instead of string I can also say it as a rope. When a jerk is given at one end of the rope, the wave pulses move towards the right end with a velocity v with respect to the observer, where the observer is at rest. So here the wave pulses travel from left to right. Now we are going to now derive the expression for velocity of transverse waves passing through the rope in the positive x-axis direction. To derive this, we have to consider a small elemental segment of the string. So this is the small elemental section of the string or the rope. Let A, B, or I can say it here also. Let A and B be the 2 points on the string at any instant of time. Let DL be the length of the small elemental segment and DM be the mass of the elemental segment. By definition, the linear mass density mu is given as mu is equal to dm by dl, where mu represents the linear mass density, which is mass per unit length. So dm is equal to mu into dl. Here the elemental string AB has a curvature which looks like an arc of a circle having its center at O, and R is the radius of this circle, such that this arc length AB subtends an angle theta at the center O. The angle theta can be written as from the equation DL is equal to theta into R, or theta is equal to dl by r. When the wave passes through the string and as we have considered a small elemental portion, there will be a tension acting in the string along the string, and there will be a centripetal acceleration supplied by the tension in the string, and the centripetal acceleration supplied by the tension in the string is given by ACP. Centripetal acceleration is equal to V square by R, where V is the velocity of transverse waves through the string and R is the radius of the small portion. Therefore, the centripetal force is given as FCP is equal to delta M into ACP. FCP is equal to delta M into V square by R. So delta m dm into v square by r is equal to, instead of dm substitute the value of mu dl. So mu v square dl by r. This is the expression for centripetal acceleration. The tension in the string acts along the tangent of the elemental string of at a and b. Here the arc length ab is very small. Since the arc length AB is very small, variation in the tension force can be ignored. Now, if you consider the tension in the tension in the string can be resolved into two components. One component T cos theta along horizontal direction and another component T sin theta perpendicular to this. So as we are having the whole angle theta, and if you draw a small segment bisector, theta can be divided into theta by 2 and theta by 2. So at the point A, the tension acting along the horizontal direction will have a component T cos theta by 2, and along the vertical direction is T sin theta by 2. Similarly, at the point B, the tension along horizontal direction is T cos theta by 2, and the tension along vertical direction is T sin theta by 2. So if you consider the case at the point A and B, the two horizontal components T cos theta by 2 at A and B are equal in magnitude but opposite in direction, so they will cancel each other. But since the elemental arc length AB is taken to be very small, the vertical component at the point A and B appears to act vertically downwards towards the center of the arc. Hence they can add up. Therefore the net radial force Fr is equal to T sin theta by 2 plus T sin theta by 2 acting at both A and B is equal to 2T sin theta by 2. The amplitude of the wave produced here is very small when it is compared with the length of the string. So sin theta by 2 can be approximately taken equal to theta by 2. Therefore Fr, the force along radial direction, is equal to 2T into theta by 2, because as theta is very small, sin theta can be taken as equal to theta by sin theta by 2 can be taken as equal to theta by 2. So Fr is equal to the force along the radial direction is equal to 2T into theta by 2. 2 and 2 get cancelled. Finally you will get Fr is equal to T into theta, but we know that theta is equal to dl by r. So theta substitute this value in this equation for theta, you will get Fr is equal to T into dl by r. But if you apply Newton's second law to the elemental string in the radial direction under equilibrium, the radial component of the force Fr is equal to the centripetal force. So we can now equate Fr and centripetal force we have already discussed. That is, we have to equate equation 11.9 and 11.12. That is, when the string is under equilibrium, the radial force is equal to the centripetal force. So I can write T into dl by r, which is the radial force, is equal to mu v square dl by r, which is the centripetal force, because the string is under equilibrium. So here dl and dl will get cancelled and r will get cancelled. So you will get T is equal to mu v square, or v square is equal to T by mu, or v is equal to root of T by mu. So it is clear that the velocity of transverse waves in a stretched string is given by the formula v is equal to root of T by mu, where T represents the tension in the string and mu represents the linear density of the string. From this equation it is clear that the velocity of the string, velocity of transverse waves in the string is directly proportional to the square root of the tension force, that is V is proportional to root T, and inversely proportional to the square root of the linear mass density mu, and it is independent of the shape of the waves. Now we can see an example. Example 11.6. Calculate the velocity of the traveling pulse in the figure. The linear mass density of the pulse mu is given as 0.25 kilogram per meter. Further, compute the time taken by the traveling pulse to cover a distance of 30 centimeter on the string. So in the diagram, it is clear that a streak is attached to one end and it passes through a pulley over the other end, and at the other end of the pulley a mass of 1.2 kg is fixed. So because of the mass is attached to this, I can say that the string is under tension. The tension in the string T is equal to M into G. A mass of 1.2 kg is attached here, so T is equal to 1.2 into 9.8, which is equal to 11.76 Newton. Given the mass per unit length mu is equal to 0.25 kilogram per meter. You are asked to calculate the velocity of the wave pulse. Just now we have seen that the expression for velocity of a transverse wave through a string is given as V is equal to root of T by mu. You know that we have already calculated the value of T and we know the value of mu. Substituting these two values in this equation, we will get V is equal to root of 11.76 divided by 0.25, which is equal to 6.858 meter per second, which is equal to 6.8 meter per second. The next question which is asked here is, we are asked to calculate the time taken by the pulse to cover a distance of 30 centimeter on the string. The time taken by the pulse to cover a distance of 30 centimeter is T is equal to D by V, where D is the distance. It is given as 30 centimeter. So 30 into 10 power minus 2 for meter divided by 6.8, which is the velocity, which is equal to 0.044 seconds, which is equal to 44 into 10 power minus 3 second, which is equal to 44 millisecond, where ms represents not meter second, it is a millisecond. Next, we are going to derive expression for velocity of longitudinal waves in an elastic medium. Let us consider an elastic medium. Here we are taking the elastic medium to be air, and this elastic medium has a fixed mass and it is contained in a long cylinder whose cross-sectional area is A and it is maintained under a pressure P. We can generate longitudinal waves in this elastic medium, say air, by displacing the fluid using a piston or by keeping the vibrating tuning fork at one end of the tube. So it is possible for us to produce longitudinal waves in the air medium, which acts as an elastic medium, either by using a piston, by moving the piston from one end to another end of the cylinder, or by keeping a vibrating tuning fork at the one end of the piston, one end of the cylinder. Let us assume that the direction of propagation of the longitudinal wave in this case coincides with the axis of the cylinder. Let rho be the density of the air that is present inside the cylinder. In this diagram, we can able to see there is a long cylinder and a gas air medium is filled inside the cylinder, so that the air acts as the elastic medium. The cylinder is fitted with a piston at one end, so that P is the pressure of the air inside the cylinder and A represents the area of cross-section of the cylinder. We can make the air inside the cylinder to vibrate to produce longitudinal waves either by moving the piston or by keeping a vibrating tuning fork at this end. And let us take initially the fluid, that is air inside this cylinder, is at rest. So at T is equal to 0, the piston at one left end of the tube is set in motion towards the right end. That is, the piston is allowed to move towards the right with the speed of u. Listen properly. U represents the speed of the piston. If u represents the velocity of the piston, when the piston is moved towards the right, the air medium, which is the elastic medium inside the cylinder, will set into vibration. So it will travel with the velocity. So we can say longitudinal waves will be produced in the elastic medium, and v be the velocity of the elastic wave in the cylinder. U represents the velocity of the piston and v represents the velocity of the elastic wave. In a particular time interval delta t, the distance moved by the piston delta is delta d. Delta d is equal to u into delta t. When the piston is moved through this distance delta d, the air inside this will also undergo an elastic disturbance, and the distance moved by the elastic disturbance in this time is delta x. So you should note that delta d represents the distance moved by the piston in a time delta t, and delta x represents the distance moved by the elastic disturbance in this time delta t. So delta x is equal to v into delta t, and you should also keep it in mind that v represents the velocity of the elastic wave through the in the medium. Let delta m be the mass of the air that has attained this velocity v in a time delta t. Therefore, you all know that density is equal to mass by volume. Here density rho is equal to delta m by a into delta x. So this delta m mass has attained this velocity in a time delta t. So from this expression I can write delta m is equal to rho a delta x. If you rearrange this equation, we will get this equation. And here instead of delta x, you substitute v into delta t. So you will get finally delta m is equal to rho a v into delta t. There will be a momentum imparted due to the motion of the piston with the velocity u. So delta p is equal to delta m into u. So delta p, the momentum imparted due to the motion of the piston, is equal to rho a v delta t into u. But the change in momentum is nothing but impulse. Therefore the net impulse I is equal to delta p a into delta t. Here how if we get this equation means impulse I is equal to force into time, but force is equal to delta p into a, the net momentum into a. So only we are getting here this as I is equal to delta p a into delta t, and so delta p a into delta t is equal to the momentum imparted here, so which is equal to rho a v delta t into u. Here a and a will get cancelled, delta t and delta t will get cancelled. So finally we will get delta p is equal to rho u v or rho v u. When the sound wave passes through the air, a small volume element delta v of air undergoes regular compressions and rarefactions as shown in the figure. That is, when the piston is moved towards the side, towards the right side, changes in pressure and volume will be created inside the gas in the cylinder, and regions of high pressure and low pressure, namely compressions and rarefactions, are produced inside the gas. So the change in the, there will be a change in the volume, so the change, and there will also be a corresponding change in the pressure. So the change in the pressure can also be written as delta P is equal to K into delta V by V, where V is the original volume, K is known as bulk modulus of the elastic medium. Here we have taken air medium, and this air medium is an elastic medium which can undergo compressions and rarefactions whenever sound passes through this medium. But V is equal to, the volume is equal to A into delta X, and you know delta X is equal to V into delta T. So volume V is equal to A V delta T, and delta V, change in volume, is equal to A into delta D, which is equal to AU into delta T. So take these two equations for V and delta V and substitute in the equation for delta P. You will get delta P is equal to K into AU delta T by AV delta T. Here A and A delta T gets cancel. So finally you will get delta P is equal to K into U by V. Now you compare equation 11:15 and equation 11:14, we will get rho uv is equal to ku by v. Here u and u will get cancelled. After rearranging, you will get v square is equal to k by rho. So v is equal to root of k by rho. So it is clear that the velocity of longitudinal waves in an elastic medium is given by the formula v is equal to root of k by rho or root of e by rho, where e represents the, e or k represents the modulus of elasticity of the medium. So what I want you to understand here is when a longitudinal wave passes through an elastic medium, if rho represents the density of the medium and e represents the bulk modulus of elasticity of the medium, the velocity of longitudinal waves in the medium is given by the formula v is equal to root of k by rho. You must understand, also know that k is nothing but v into delta p by delta v. Let us take see three different cases. Case 1, for a solid medium, if the medium happens to be an one-dimensional rod, then here there will be only Young's modulus will come into part. So here y, for a one-dimensional rod, velocity v is equal to root of y by rho, where y is the Young's modulus of material of the rod and rho is the density of the rod. The one-dimensional rod will have only Young's modulus. But if you take the case of a three-dimensional rod, the speed of longitudinal waves in a solid in three-dimensional rod is v is equal to root of k plus 4 by 3 eta by rho. The formula will get altered, but where eta is the modulus of rigidity, modulus of elasticity of the material of the rod, k is the bulk modulus, and rho is the density of the rod. If you take into account of the liquids, for liquids or any gases, v is given as root of k by rho, where k or b or e is the bulk modulus and rho is the density of the rod. Now let us see two examples. Example 11.7. Calculate the speed of sound in a steel rod whose Young's modulus y is equal to 2 into 10 power 11 Newton per meter square and density is 7800 kilogram per meter cube. So v is equal to root of y by rho. Here only one-dimensional rod is given. The value of y is 2 into 10 power 11, which is Young's modulus, and rho is 7800. So v is equal to root of 2 into 10 power 11 by 7800, which is equal to root of 0.2564 into 10 power 8. which is equal to 0.506 into 10 power 8 4 meter per second, which is equal to 5 into 10 power 3 meter per second. Therefore, longitudinal waves travel faster in a solid than in a liquid or a gas. Now you can able to understand why a shepherd checks before crossing a railway track with his sheep by keeping his ears on the rails to safeguard his cattle. The next example is example 11.8. An increase in pressure of 100 kilopascal causes a certain volume of water to decrease by 0.005% of its original volume. So here the change in pressure and the percentage change in volume is given. You are asked to calculate the bulk modulus of water, and also you are asked to compute the speed of sound waves in water. Let us see the solution. Bulk modulus B is equal to V into delta P by delta V. Here delta P is given as 100 kilopascal, that is 100 into 10 power 3 pascal, and here the percentage change in volume is given, but we want here V by delta V. What do you mean by percentage change in volume? That is delta V by V into 100 is given as 0.005, but in the problem we want V by delta V. So delta V by V is equal to 0.00 by 5 by 100, which is equal to 0.005 into 10 power minus 2. As we want V by delta V in this formula, we can reciprocate this. When you reciprocate this, we will get V by delta V is equal to 1 by 0.005 into 10 power minus 2. So take this and substitute in this expression. We will get B is equal to 100 into 10 power 3 divided by 0.005 into 10 power minus 2, which is on simplifying you will get it as 2000 megapascal, MPa, where MPa is called as megapascal. Mega means 10 power 6. The next part is the speed of sound in water is asked. So V is equal to root of K by rho, which is equal to the value of K or bulk modulus is 2000 into 10 power 6 divided by 1000, which is equal to 1414 meter per second. So as consolidated fact I told you, I want you to remind you that when a transverse wave is produced in a stretched string, the velocity of transverse waves in a stretched string is given by the formula V is equal to root of T by mu, where T is the tension in the string and mu is the linear density of the string. When a longitudinal wave passes through an elastic medium, the velocity of the longitudinal wave through the elastic medium is given as V is equal to root of K by rho, where K represents the bulk modulus of elasticity of the medium. Suppose if the medium happens to be a solid medium, when it is one-dimensional rod, the formula to calculate the velocity of waves in one-dimensional rod is given as V is equal to root of Y by rho. Okay, thank you.